In this session, I'm going to show you some analysis for the mole inside a rectangular resonator with conducting walls. I want to bring out this picture from lecture 11. In this picture, you see a TM mole propagating along Z direction inside a waveguide. And for this parallel plate waveguide, we have open boundaries on this end and also on this end. But to define a TM mole inside this waveguide, we have to define a reference axis along the propagation direction. Therefore, if we have a Z component electric field along this reference axis, we call the mole propagating inside to be a TM mole. Similarly, we also define a TE mole inside this waveguide with reference to a propagation direction Z. And so if we have a magnetic field along Z direction, then we call this mole to be a TE mole or transverse electric mole inside this structure. Similarly, if we want to define a TE or TM mole inside a resonator, we need to choose a reference axis. So to ease the discussion, we choose the reference axis to be Z direction. But be careful about the choice of the reference axis. When you choose a different reference axis, a TE mole or a TM mole inside a resonator can become a different mole. So for now, let's just choose the reference axis to be along Z direction. Although along Z direction, in fact, you have standing wave instead of propagation wave in that direction. And also, this is the field pattern of the TM11 waveguide mole we used previously. Now, if you want to convert this mole into a mole inside a resonator, in practice, you can just put two boundaries at this end and create a rectangular box. And then the field pattern, in fact, will also change. But by doing this, the mechanical construction, you can create a box for storing electromagnetic energy inside. Now, you put two boundaries along Z direction, so you'll be expecting to set up some standing wave along this direction. So let's continue to write the waveguide mole field EZ and create two waves, one in the forward propagation direction along Z and the other in the backward direction along minus Z direction. So you do a superposition of this component to form a standing wave along this direction. But originally, this sign solution already tells you the standing wave along the transverse direction. At this moment, we don't know yet if we want to keep this plus sign or minus sign in this expression, but this is going to be decided later by using the boundary conditions. But don't forget that when we write down this solution, there's a dispersion relationship that is H squared equal to omega squared epsilon mu minus beta squared. And this H squared was already determined from the waveguide analysis to be the sum of these two values. And this is basically the K constant along the X direction, and this is a KY along Y direction. Now, let's look into the boundary conditions. We wrote down the expression for the Z component of the electric field. So we're going to look into the Z surface. For example, for this Z surface, you'll be expecting to have a maximum value for the electric field normal to this Z surface. We just reached this conclusion in the last session or in previous lectures. So the choice of this plus minus sign is to create a maximum value of the normal component of the electric field on this surface and also on the surface opposite to this one. So we'll choose the cosine solution and make sure that the length of this cavity is the integer multiple of the half wavelength along this direction. So you come up with this eigenvalue p pi over a for this beta value because you create a standing wave inside, and this p is the integer that can be 0, 1, 2, and so on. But there's some restriction on m and n, because if you have 0 value for m or n, then this term easy disappear. So you cannot choose m to be 0 or n to be 0 in this expression. So this means that for Tm mole inside this box, m cannot be 0 and n cannot be 0. So once you determine this the beta value to be p pi over d, then you can put this beta value into this dispersion relationship. Just specify this beta to be equal to p pi over d. Then you can calculate the resonant frequency inside this box. And if you do some algebra, quickly you can come up with this expression. F mmp mole will have a resonant frequency equal to this. And this frequency is specified by the dimension of this box. At the same time, specified by the integer values of m and p. And be careful that the p can be 0, but m and n cannot be 0. For example, we can specify this p to be equal to 0, try to minimize this resonant frequency, but m and n cannot be 0. So the minimum value of this the resonant frequency is going to be equal to this by specifying this p equal to 0. So you have this value with m equal to 1 and n equal to 1. So this is the resonant frequency for the TM110 mole, and this is the lowest frequency of the TM mole inside this resonator. So we call this dominant mole of this cavity for the TM field. Once you have the Z component electric field, now you can calculate all other field components from the Z component electric field. For example, you can calculate the X component of electric field given by this expression. And this expression appears tedious, but in fact, you can extract some physics from this expression. The Z component electric field points toward this X direction, and this field component is a tangential component with respect to this Y surface and also this Z surface. And this surface is called Y surface because the surface normal direction is along Y direction. And this surface is called the Z surface because the surface normal of this surface is along Z direction. And on these two surfaces, the field Ex has to go to 0 because tangential component of the electric field on a conducting boundary has to be equal to 0. So you see the sign solution along Y direction and also along Z direction. And if you look into the Y component of the electric field, this Y component is along this vertical direction. And this field component is tangent to this X surface and also the tangent to the Z surface. So you expect the sign solution along X direction and also Z direction. On the other hand, when we look into the magnetic field, the physics is a little bit different because the tangential component of the magnetic field will induce the surface current on the conducting boundary. So they have the cosine-like solutions on the boundary. For example, this the X component magnetic field along this direction. So the surface current is going to flow along the Z direction. So the tangential component of the magnetic field on this surface and also on this surface will give you cosine solutions. So you see this, the h of x will have cosine dependent on y and z directions. Similarly, if you look into this, the y component magnetic field pointing upward in this direction, and this direction is the tangent to this surface and also this surface. This surface is x surface, and this surface is z surface. So along x direction and z direction, you have cosine solutions. And be careful about setting the value for m and p, those small numbers, because, for example, if you set n equal to 0, then this term drop to 0. And there's also n dependence in this expression. Ey will also goes to 0. And you see n here, if n is equal to 0, then hx also disappear. And this n is inside the sine expression, hy will also disappear. So this means that the n cannot be 0. Well, similarly, if you set m equal to 0, everything will also drop to 0. So there's a condition that neither n nor m can be 0 in these fields. 所以呢，在这个小节里头，我介绍了TM mode 在 rectangular resonator 里头的一些物理特性。那定义这个 TE 或 TM mode 的时候呢，必须要有一个 reference axis。在我们的分析里头呢，是取 z 的方向当做是这个 reference axis。但是如果你的定义不一样的话，那这个 mode 的 definition 不会是单一的。那我如果有一个这个rectangular box， 它的三边的这个长度是 A、B、D 的话，那它的 resonant frequency， 这个 TM mode 的共振频率的话呢，可以表示成这么一个形式。但是很小心，这个 P 可以等于0，但是 M 跟 N 不能个别等于0，或者是全部等于0。那所以呢，这个dominant 的这个 TM mode 呢，前面 M 跟 N 最小值就是1，那但是 P 呢可以等于0，所以这个 dominant mode 的这个 mode frequency 呢就是 TM110。这是这个小节里头的一些重点，谢谢。